Welcome back. We're going to rehash a little bit in this video. I received a comment, just one comment, um, from a viewer calling me out saying that I don't know what I'm talking about. Okay? We'll leave it at that. You have the right to your opinion, so on and so forth. You have to back it up with facts, right? So, in addition to the previous videos I had mentioned, a YouTube creator, somebody that I've followed along with for quite a few years, he doesn't necessarily take the easy route to the final assembly of an engine. But recently he has run into problems and he's duplicating those problems with his next build. So, in order to help all of you out, to help understand this and break it down to clarify exactly what I've shared with you, you have to understand the metallurgy makeup of the components of an engine in order to finalize the build. You can depend on different catalogs or instruction from manufacturers, but you yourself, if you are assembling the engine, need to understand what it is and the components you're using, the different expansion rates, to dictate which one of those informational sources is correct. So today we're going to go back over piston and wall clearance. Okay, just to rehash this, I did it in a couple videos ago, but it seems like we need to re-emphasize some of the things going on. The difference between cast iron cylinder blocks of yesteryear compared to new aluminum blocks with steel liners, and the different piston manufacturers, what they're recommending for cylinder wall clearances, so on and so forth, also dictated by engine oil. Okay, so I have another prop to explain what our EPA, our Department of Transportation, what they're doing with the newer engine oils. So every manufacturer, if any of you own a newer car, say after 2005 or so, you'll notice that most of the engine oils from a stock vehicle are in that 5W or OW rating. Why has the EPA or the automobile manufacturers gone on to that? So I don't have laundry detergent, but when you hear the word of detergents being added to the oil, it's for the cleaning aspect. Okay? So, for instance, Royal Purple, the manufacturer oil of Royal Purple, has a very high concentration of cleaning detergents in it. So even if you have an older engine that has, maybe you've gone by the manufacturer direction of changing your oil up, anywhere from 6 to 10,000 miles, the crud that builds up on your engine, you can actually do a Royal Purple oil change, and within the next oil change, it will actually remove some of those deposits to the point where you can pull off the valve cover and actually see the difference of the deposits being left behind. The Royal Purple, the high detergent, will help kind of clean it out. Now again, Royal Purple being a man-made synthetic, okay, it's high in petroleum or high in detergent content. When you listen to these oil geeks that are online, okay, they've even admitted that the OW and 5W engine oils do not include detergents. Okay, let's make that very clear. Now, in a previous video, I also mentioned that the viscosity of the oils have a reduced compression protection. So if you're squeezing the oil between two components at a very high rate of speed, they will collapse or be shed out, squeezed out of the tolerances within the rotating mass to the point where they don't provide as much protection. Something that has cost billions of dollars to General Motors today with their most recent engine design of 2023-2024. They're having a recall because of failure. A lot of the tolerances built in. So, okay guys, General Motors, one of the largest auto manufacturers in the world, even their engineers are making mistakes. So even depending on some of the highest names in the industry, whether it be Keith Black, JE, Mahl, all the different piston manufacturers, can you necessarily trust their recommendations? You have to be responsible for the build that you're doing. And if you're a race engine builder, you should have the experience and know how to mix the different components and how they're going to work together. It's that simple. So one of the props I have here today is obviously just some car wash. Okay, so detergent, some soap. Now, one of the reasons the EPA has instructed the auto manufacturers to go to a thinner oil is because when it does make its way into the combustion chamber and mixes with the petroleum fuel, it will ignite. Okay, very thin oil, a petroleum product with a thinner viscosity is going to be much more flammable in a thinner form. Okay, so any one of you that were around during the 70s and 80s, when engines started to break down and the thicker oils would blow by or get past the piston rings, you would have smoke coming out of the tailpipe. Okay, blue smoke would show a rich condition. Obviously, a lot of oil getting through. The newer cars being equipped with catalytic converters, you're not going to notice as much. Or if you add a can of, sorry, I got a fly buzzing around here, so it distracted me. Any of the fuel or oil additives to help clean in the engines, seafoam, it's going to immediately attack those deposits and release them into the exhaust system and even clog up your catalytic converters. So, understanding detergents. Man-made detergents, soaps, okay, are they flammable? No, okay. I could take a lighter out right now, pour this detergent, the soap, and put a flame to it, and it's not going to ignite. You could do this with like your Tide laundry detergent, so on and so forth. So if you have a OW or a 5W motor oil with a lower viscosity rating, it has a bigger tendency to make it past the oil control rings, piston rings, within the wall clearances, so on and so forth, and be exposed to the combustion chamber. In order for it to be ignited, it can't have a certain chemical makeup of detergent. It's non-flammable. Okay, so all of the newer vehicles that are recommending, as you take off your oil cap and read it, so on and so forth, it'll say recommended 5W or W30 oil. It's to the extended life of the engines. Once they start to wear out and oil seeps into the combustion chamber, the engines are still able to ignite it and pass it through the exhaust system. It's that simple, folks. The EPA, mainly areas of the United States that have very high traffic areas like Los Angeles, where vehicles are constantly at a standstill. There's a high concentration of vehicles releasing the carbon into the air. The smog that is related to those communities is being blamed on this type of material being released into the air. It's that simple. What's happening in California eventually bleeds out into the industry. During the 1980s and even 1990s, one of the reasons why the Mustang Fox body was such a popular choice for modifications, California had all kinds of different regulations, all right, more than any other state. Now, there are certain territories within bigger cities like Chicago, Minneapolis, that also mandated the same kind of practices. Or the East Coast, a lot of your vehicles had to go through an inspection with the exhaust sniffers to see how much oil is actually being burnt with the exhaust gases. All of that made the manufacturers, the insurance companies, EPA, design the engine oils to be a thinner viscosity, so they will actually burn along with the petroleum fuel that's in the combustion chamber, so it can be released to the air with less impact, less of a carbon footprint. The engine oils are not designed of that viscosity level to actually protect on the engine. The thinner viscosity oils will also swipe or be released from the engine components, carrying some of the heat of the engine to the oil pan before being reused again. So it is to address some of the frictional heat exposed to an engine and allow it to shed it with the engine oil. The thinner the oil, the faster it sheds from the components. Now, with thinner oils, tighter tolerances can also be incorporated into the engine. Now, I'm going to give you an example for any of you that are water enthusiasts, whether you're a jet skier, or excuse me, not a jet skier, water skier. You realize that when you come out onto the plane of your, whether it be a water board or skis, you realize the layer of water that actually holds you up. It's the pressure being squeezed in between that. If you're on the ocean, being salt water, the consistency of the water is thicker. It doesn't take as much to get up on that plane. But in order to draw you through the water, it actually takes more power because there's more resistance incorporated with water compared to if you're on a freshwater inland lake, where it takes you a little bit more effort to get up on the skis or wakeboard, whatever is underneath you, okay? And it takes less power from the boat to actually pull you through it. There's less resistance. That boundary layer being created is no different than the oils. A higher viscosity oil is going to be more similar to the salt water of the ocean. A thinner viscosity motor oil is going to be more similar to the freshwater, clear, no salt content waters of inland lakes. So even if you're not an automobile enthusiast and you understand how skiing works, or even winter snow downhill skiing, you understand that the softer the powder, the more it compresses. If you have a hard pack, you go faster, correct? So if you are from Colorado and you're one of these downhill skiers or snowboarders, you realize the more slick the snow is, the faster you go, the less resistance there is. Same with oils. Okay, just get that out of the way. So the tighter the tolerances requires less of the oil material to slide upon. So the less friction, so on and so forth. But the compression of that boundary layer of material is reduced with the lower viscosity oils. Okay, so let's just get that out of the way. If anybody wants to debate that, go right ahead. Okay, time proven. That is what our EPA is demanding from our manufacturers. It is not because our oils have become better. Period. Now, with that knowledge, let's go back to the engine building and piston expansion rates, including the other materials, because I'm seeing these problems duplicated across the internet, whether it be YouTube channels, Facebook, you name it. So, here on this picture, we have basically the top view of the cylinder and the piston. The gap on around the entire perimeter piston is your clearance area. Piston wall clearance. In a previous video, I mentioned if you use the calculated formulas, the bigger the bore, the larger the gap needs to be. Okay? The formula of using 0.002 times the actual bore diameter, not the piston, the bore diameter, will bring you normally in that 8 to 10 thousandths range for your typical muscle car engine, from a 350 to a 455. In that range, anywhere from 8 to 10 thousandths. So, for you unmathematician type individuals out there, we need to know the positions of a caliper to understand where that number falls. Everything to the right of the decimal. Okay? Whatever number you have, it starts with tens, hundreds, and thousandths of an inch. So you can go to any one of the piston manufacturers' websites and look at their recommended clearances. The smallest number that I've seen any of the manufacturers recommend is a 4.5 thousandths clearance. Okay, that's the bare minimum. Okay, easy enough. Bare minimum. Some of the piston manufacturers or YouTube creators are following the direction and using only the one number. 2000s. That is actually what they're using for their clearance between the piston and the wall. 2000s. You are half, more than half of the minimum requirement used for piston and wall clearance. Now, this goes into the metallurgy of the different aluminum piston designs, whether it be cast, hypertonic, or forged. They also have two primary aluminum combinations of recipe between the 2618 and 4032 aluminum mix. That is going to be the higher concentration of nickel, how close and compressed the component is, and how many heat cycles it's been exposed to help forge it. Easy enough. So they all have a different expansion rate. 2618 has a larger expansion rate. That's going to be your typical cast or hypertonic piston. The 4032 is going to be more of your forged piston. Now, at 100 degrees, not the realistic temperature within a combustion chamber, pistons are tested at 100 degrees. From a cold state to 100 degrees, a 4032 piston will expand 4 thousandths of an inch in diameter. So if you were installing an engine with only 2 thousandths cylinder or piston to wall clearance and it's exposed to 100 degrees, you're already causing the piston to pinch inside of the cylinder wall. Folks, when I see engine builders, whether it be your do-it-yourselfer or somebody that gets paid to actually assemble engines, and they're throwing out numbers like this, I watch to see the destruction immediately upon startup. Because what's the temperature in a combustion chamber? Is it 100 degrees or is it severely escalated from that? Okay. It will expand more than this when it's actually exposed to combustion chamber temperatures. And the higher the compression or the addition of a power adder such as nitrous oxide or forced induction turbos or superchargers, the heat will be much higher than that. The expansion rate is almost going to be double this amount. Okay, so you can do the math. If you take 0.002 times the cylinder bore, not the piston, the cylinder bore, that will give you the needed cylinder wall clearance for your application. And it's going to be precisely told to you whether you're using the different metal component, the aluminum mix, or the different coatings that are added to the pistons. Now, a skirt material will normally add about 3 thousandths to the overall diameter of the piston. Can you do the math? Okay. 8 to 10 thousandths for a typical cast piston for a standard 4-inch bore. 8 thousandths being a standard bore, 30 over, is going to bring you to the needed 12 thousandths, okay? 10 hundredths thousandths. Notice there's only 1 0 between the decimal point and the first number. Now, if you're installing an engine with 2 thousandths of piston to cylinder wall clearance, what's going to happen as soon as that piston is exposed to heat? It's going to bind within the cylinder. That's exactly what I mentioned in the previous video. And this creator, this engine assembler, is duplicating it with another engine build. So I'm just following along because I know what's happening. I know exactly what's going to happen. As soon as the engine is brought up to operating temperature, there's going to be additional friction or even lockup within the rotating assembly. There is not enough cylinder wall clearance. Period. Even to the point where your thinner motor oils of OW or 20W30 is not able to even seep into the grooves or the clearances between the cylinder wall and the piston. Again, calling out these oil geeks of the wall finishes, the amount of oil that it can carry to allow the piston to have a barrier of oil to lubricate itself. The tolerances are getting so tight from some of these engine builders, even the thinner oils cannot seep into the areas and actually provide that lubricating surface. Now, in addition to that, things that we practiced on cast iron engine blocks is totally different than newer generation late model engines. The material of the engine block and the cylinders themselves is changing. So, a little bit of homework for you. What expands more underneath heat? Cast iron or steel? Going back to the muscle car era, okay, prior to say like 1987, okay, when aluminum blocks started becoming the mainstream of the manufacturers, cast iron blocks. A cast iron block is formed of the exact same material. It's cast iron. So even the cylinder walls are also cast iron. Newer late model engines will have an aluminum casting with a steel sleeve installed into them. So there's a different expansion rate out of even the materials of the engine blocks. So if you're buying pistons and you tell the manufacturer, I'm working with this platform, they should be able to say, hey, oh no, our pistons expand this much at a certain rate, say 100 degrees. The material you're working with in your block is going to have a different expansion rate to the newer late model engines. So aluminum blocks with steel sleeves, the aluminum will not expand as much because it is able to radiate the heat out. The steel sleeves will expand greater than the aluminum. But the steel sleeves will retain their expansion rate or their shape better than a cast iron cylinder. So if you are building something of the muscle car era and you are taking the most modern piston manufacturer recommendations for cylinder wall clearances of 2000 and you're installing it in a cast iron block from yesteryear, you're guaranteed to have a lockup. Guaranteed. Now, this is what I found to actually be the most correct ratio when working with older cast iron blocks and using the most modern day forging pistons. Instead of using the formula multiplier of 0.002 times the bore, if you're working with older cast iron blocks and cylinder walls, you actually need to add the 0.004 formula into your bore. Because the pistons are not going to swell as much as a cast piston, the forged high performance pistons, but the cylinder, the block itself, is going to expand at a greater rate, especially in high performance applications where cylinder temperatures are on the increase. Now, if you notice the makeup of every engine block out there, from bottom dead center to top dead center, the cylinder is supported in a different manner. Normally, the deck surface, the thicker the deck surface, the more retention it has to remaining in that pure circle. The bottom of the cylinder, reinforced by the webbing of the block, also has reinforcements. But the water jacket area of the cylinder wall will actually flex. It will be allowed to expand further. So even if you take your engine block to a machine shop and they do a plate, excuse me, I have to think about this for a second. A torque plate honing practice. When the bolts, the head bolts are going through the block, they will compress the cylinder walls to the point where they might deviate in or out, concave or convex. It's putting that preload in there with that 100 plus pounds of head bolt torquing. Then the process of boring the block or honing the block is done. It is causing the cylinders to deform under the pressure and giving you a true cylinder circle. The moment those torque plates are taken off, they will go to the relaxed state. So even if you're an engine builder and you are miking out the cylinder bores without the torque plate on it, your cylinders are not going to be perfectly round. You have to take the lowest, the smallest measurement and use that as comparison to your piston diameter, using a formula of 0.004 times the cylinder bore in order to achieve the correct cylinder wall clearance. That simple, folks. So not only is the engine oils designed to be burnt in the combustion chamber, they're not providing the lubricating layer needed to fill in that larger cylinder to wall clearance. Now, piston rings. Okay, folks, piston rings have obviously gotten smaller in thickness. Okay, so from 11, the standard cast iron piston of yesteryear to the smaller 1 millimeter, or 1.5 millimeter piston rings, the pistons have gotten bigger to fill in more of that piston to wall clearance because of the thinner viscosity oils. Okay. The expansion rate of the pistons and the steel cylinders are closer in proximity of each other. Okay. If you are taking today's modern recommendations from the piston manufacturers, installing it into an older cast iron block, no matter what machining practices you put into place, you cannot follow the piston manufacturer's recommendations. Almost every single one of them will give you the 0.002 number. If you're not intelligent enough to know that that is just the multiplier, I hope every engine you build blows up. Now we can take this to the extent of the highest performance level known in the automobile industry, Formula One. A Formula One engine needs to be up to operating temperature before the pistons or piston rings can seal off the cylinder. Up to that point, there's massive clearances. Because of the extensive RPM, sometimes 20,000 RPM in some circumstances, and the massive amounts of heat being exposed in the combustion chamber, the pistons swell and the cylinder wall swell. Because remember, expansion doesn't just go from inside out, it goes in both directions. So a cylinder wall doesn't only expand into the water jacket or into the engine block, it also swells into the cylinder bore itself. Formula One engines typically use more than 2 quarts of oil just in warm-up. That's how much oil escapes around the piston and goes into the combustion chamber until the engine is up to operating temperature. So a good question. How many piston rings are in a Formula One piston? Do they have an oil control ring? Nope. Do they have a second ring? Nope. They're installed with one ring. The top of that ring is responsible for controlling the blow-by, the compression gases. The bottom portion of that exact same ring becomes the oil control ring. The cylinder distortion allows oil to actually be fed in between the piston ring and the cylinder wall at approximately half the travel of the piston within the cylinder bore. It actually opens up enough to allow oil to seep in between the piston and the cylinder wall and the piston ring, so that on its travel back up, it has a lubricating aspect. It is the compression pressure chambers that help the oil stay down. Some of it still migrates into the exhaust or into the combustion chamber. They are using thinner viscosity oils so that it burns off with the fuels being introduced. Okay, folks, everything that occurs in elite racing, from engines to transmissions to suspensions, make its way into the engineering of our daily drivers. That's the truth. The racetracks are the R&D for your manufactured vehicles. What happens on the racetrack finds its way into your daily driver. Through brakes, tire technology, engines, exhaust, oils, it all starts in the elite racing and it rolls downhill. If you don't understand this, okay, you have no excuse to not check this out. So you can go on the websites of either Keith Black, JE, Mall, and look at what the recommendations are. Are those recommendations for the most late model engines with aluminum blocks and steel sleeves in the higher content aluminum forged pistons? Or are they designing their pistons to work with older cast iron engines? And when you're using older cast iron engines, is it a Ford engine with a higher nickel content that has a reduced expansion rate compared to a full out cast? You need to know the materials before determining your required clearances. Have a good one.